The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
If you project that a certain part of the world is going to be hit twice as often, and you know for a given storm how much that's costing dollars or risk to life, then suddenly you can attribute, you can say, well, the raised CO2 in the atmosphere is costing us X $million extra per year.
Later on, we'll speak with Chris Huntingford, a climate modeler at the Centre for Ecology and Hydrology in the UK, about just how we go about modeling an entire planet's climate. But first, let's look at something a little more familiar to our everyday. Weather forecasts, how they work, and how we know when severe weather is on the way. Welcome to Science for the People. I'm Rochelle Saunders. With me is Rick Smith. Rick is a warning coordination meteorologist at the National Weather Service Forecast Office in Norman, Oklahoma. He manages NWS Norman's decision support services and hazardous weather preparedness and outreach programs. Rick, welcome to Science for the People.
It's great to be here. Thank you for having me.
I'm always curious when I first connect with people, how did you get into weather forecasting in the first place?
Oh gosh, that's an interesting question, and one that a lot of meteorologists seem to have a similar origin story or backstory. A lot of meteorologists that I work with have been interested in weather since they were kids, and that's certainly how I started out. Many weather people have a story where they were impacted by a blizzard or a tornado or a hurricane, and that sparked their interest. I don't really recall a specific event. I just know that as far back as I can remember, in kindergarten, first grade, I've been obsessed with the weather and interested in learning more about it. And that's kind of been my path all the way through life.
So for something that I think everybody knows about, a weather forecast, I mean, I look up a weather forecast pretty much every day, whether it's to figure out what my day's weather is going to be like or what the weekend is going to look like for some event I'm planning or outing I'm planning. But me and probably most other people who do this every day don't really have a good idea of what goes into making a weather forecast. So can you tell us a little bit about how you do what you do when it comes to creating a weather forecast?
Well, it is a very complex process. Weather is a complex phenomenon, and it involves air and water. It involves a fluid in the atmosphere. Air is a fluid, and trying to forecast what's going to happen even an hour in advance sometimes can be challenging. And in the National Weather Service in the United States, we do weather forecasts out to 7 days routinely. Those weather forecasts begin with a meteorologist or a team of meteorologists looking at all kinds of weather information. And really the basis for forecast is what's going on right now, the observations. So we're looking at things that we can measure. When you look at the weather, you see the temperature is 64 degrees, it's cloudy. Those observations are typically taken at an airport somewhere. So we are looking at all those weather observations, not just in the area that we are responsible for, but all over the country and in some cases over large parts of the world, because what we're forecasting to be here in 5 to 7 days may be out over the Pacific Ocean or somewhere like that, further out, that far out in the future. So we're looking at the observations and measurements that we take at the surface. But weather forecasting also involves looking at the three-dimensional structure of the atmosphere. So it's not enough to know what the temperature is and what the humidity is here at the ground. We have to have some idea of what that is hundreds and thousands of feet above our heads. And really one of the only direct ways we have to measure that is through weather balloons, which we've been doing for many, many decades. It's a kind of an old school technology, but we attach an instrument package onto the bottom of a balloon, and we let that go. And we take the readings that instrument package sends back to us, and those go into our initial assessment of the atmosphere as well. So weather forecasts always start out with looking at what's happening right now. This is
something that has fascinated me about weather forecasting ever since I was sort of aware that it was the case, the idea that a place's local weather can be massively impacted by what's going on quite far away. So I'm curious, when you're looking at trying to predict weather in your local area, how far out do you generally look for a place like let's say Oklahoma, are you looking just into the sort of surrounding states? Do you have to look farther out into the country? Is it even farther out into the oceans on either side of the country? Is there sort of a pattern for Oklahoma where the weather tends to come from one area rather than another?
Well, sure. And it really depends on what type of weather we're forecasting or what we're expecting to happen. During the springtime, when we get most of our severe weather and thunderstorms and tornadoes and things like that, very often we're looking at storm systems that really may not even be in existence yet. Another thing that we use in forecasting, a big part of forecasting, is computer models. Computer models take all those initial observations and they run a series of very complex scientific and mathematical equations based on the laws of physics and the equations of motion and all these types of things. And then that produces a forecast or numerous forecasts. So very often when we're trying to forecast a weather system that's going to be here, let's say in 5 days, that weather system is not even in existence yet. There's not even an area of low pressure there yet. But what we're seeing maybe out over the central Pacific Ocean, we're looking out that far. The computer models are showing us that based on all the data that's been input to those models, that a storm system could develop. And so very often we don't know for sure what's going to happen with that storm system until we start getting some of those direct measurements. So we are looking all the way out into the central Pacific Ocean quite often for storm systems that are going to impact the central part of the United States. But it's not really until those storm systems or developing systems get onto the coast where we start getting into the network of observations, the weather balloon network and the surface observation network, where we're going to be able to see those. So it is. You are dealing with air and water here and forecasting it many, many hours and days into the future. So we are looking as far out as we need to look to see if we can get our first glimpse of that and try to get a handle on where it's headed and what it's going to do.
That weather balloon network, is that managed by a bunch of different organizations that share data, or is there a sort of overarching organization that kind of manages that system of weather balloons?
Well, interestingly, the weather balloon network is a worldwide network. So there are entities in different countries all across the world that are launching these weather balloons. And we actually coordinate the times of those routine launches. In the United States, the Weather Service launches all the weather balloons routinely, and we launch those 2 times a day. And those are times coordinated all over the world so that the observations that we get from those weather balloons kind of sync up in time as best that they can. So we're looking at similar data at the time of those 2 routine launches. So yeah, here we're looking at the National Weather Service who launches those weather balloons routinely twice a day. There are other entities that launch them, maybe military installations or researchers are launching weather balloons. But here it's the Weather Service, National Weather Service's balloon network that provides a majority of the data.
You mentioned low pressure areas, and this is something that if you watch weather reports on, especially on TV news, we hear a lot about low and high pressure. I admit to not really understanding how that works. So is there like a primer you could give me on low pressure versus high pressure and how that kind of makes predictable weather?
Well, it gets complicated. Obviously, meteorology is a complex topic, but generally speaking, and this is super simplified, areas of low pressure are more typically associated with bad weather. Areas of high pressure are more typically associated with more fair weather. When we have an area of high pressure in the atmosphere, and let's say we're talking at high pressure at the surface, that's typically associated with generally fair weather. So we don't usually get thunderstorms and tornadoes and blizzards and things like that associated with an area of high pressure. That's almost always associated with low pressure. But the two always exist, and it just depends on the location of those areas, the intensity of those, and that really determines everything from who gets rain or snow, who gets tornadoes or no thunderstorms at all, how strong the winds are, how heavy the rain is. Obviously, again, very simplified, but when you're looking at low pressure versus high pressure on a weather map, low pressure is typically the worst weather.
I'm also curious, over the last couple of decades, is our ability to forecast weather with better and better accuracy improved a lot, or is it sort of something that we figured out how to do a little while ago and we've just been doing with the same kind of accuracy? I'm curious in part because people always kind of complain about inaccurate weather forecasts. Obviously, we only remember when it's inaccurate and not when it's accurate.
Exactly. And meteorologists are used to that in life. You know, we don't hear about the successes, but we really hear about the failures, including our families at home. They'll let us know if they're upset, if that snow forecast didn't materialize and they ended up having to go to school or whatever. But weather forecasts on average have gotten better, and they have been getting much better over the years. A forecast today that goes out 5 to 7 days is as accurate as a forecast that in the past that went out 2 to 3 days. So certainly it's not perfect, but we are getting much better. The accuracy of the temperature forecast, the accuracy of the precipitation forecast, and certainly the accuracy of our warnings and watches and the information that we provide to alert people about bad weather, including thunderstorms, tornadoes, winter storms, and things like that. All of those statistics continue to improve as we go through time. And that's really a testament to many things. One of the things is obviously at the core of all of this is a human forecaster. You know, we have computer models. The computer models just give us one or several scenarios of what might happen. It's still up to a person, an expert meteorologist, to look at that data and determine what's happening. The computer models continue to get better too. So really the forecasting system as a whole has continued to show improvement over the past several decades, and especially in the past few years.
Is there a formal process or a formal set of kind of historical data maybe where communities of meteorologists can sort of look and see, are we improving? Was this a particularly bad year for prediction? Is there a new technique that's showing a lot of promise for predicting weather events?
Well, we're all about verifying our forecast. So a good meteorologist will always check to see how good their forecast was. And that's a routine part of our operations. We've been doing that for a long time, and we have quite a long history of data to look back at and compare current forecasts to. So if we're forecasting temperatures, then we know what the temperatures were at these select observation sites around the country and around the world, and we can compare those. And that's what we do. Really one of the most promising tools that we're seeing, we continue to see the computer models improve. And a computer model, again, just takes the current data and it knows how the atmosphere is supposed to behave. And then it projects outward. It could be 1 hour in the future. It could be 10 to 14 days into the future, what it thinks the atmosphere is going to look like at many different levels. Those computer models continue to get better. And one of the types of models that we use a lot here in the central part of the United States is when we're forecasting thunderstorms and potentially tornadoes, is there are computer models now that not only tell us where the big, broad, low pressures and high pressures might be, but these computer models are getting down to the storm scale, where it gives us a picture of what a radar display might look like several hours into the future. Again, it's not always perfect. It's not always 100% accurate, but we've had some really amazing forecast successes using those computer models where we see persistent signals in the models that continue hour after hour to develop thunderstorms over a certain area, a certain type of thunderstorm. And we've actually made forecasts based on those and given people a lot of advance notice about tornadoes and severe weather that occurred later in the day. So I'd say computer models, and especially some of those what we call short range computer models, those high resolution models that are looking at that storm scale, just continue to get better and better.
I do want to talk more in detail about severe weather because I think it's a point of fascination for a lot of people, these kinds of severe weather, especially when we get into the topic of things like tornadoes. What kid hasn't been fascinated at some point by a tornado or the idea of tornadoes? So I'm curious, at what point does a storm transition from being a sort of normal, typical storm to a severe storm? Is there a particular definition of what severe means?
Well, it depends on who you're talking to. When you're talking to meteorologists here in the United States, we have a very strict scientific definition of what a severe thunderstorm is. Severe thunderstorm is one that produces hail that's 1 inch in diameter or larger, and or winds of 58 miles an hour or higher. So if it's got either of those two things, then we call it a severe thunderstorm. Now, the generic term severe weather can be used to include any number of things. When we say severe weather as meteorologists, we're thinking of those severe thunderstorms. We're also thinking maybe of tornadoes and maybe lightning and things like that. But it's primarily the tornadoes and severe thunderstorms that we think of. Now, the people that we're forecasting for, the general public, probably doesn't think of that scientific hard edge definition that we have. So many people, severe weather could be heavy rain. It could be lots of lightning. It could be small hail. It could be gusty winds, scary looking clouds. So the communication of information, that's one of the areas where our definition of severe weather may not match up exactly with what the average person's definition is.
I'm not sure how frequent something like this would happen in Oklahoma, but I'm assuming something like a blizzard would be classified as severe weather as well?
It could be a severe winter weather. Again, depends on who you're talking to. But I think to most people, it would be a severe winter storm. Again, it depends partly too on what part of the country you're in. I mean, when I say severe weather here in Oklahoma, people think of tornadoes and hail and wind. They don't necessarily think of blizzards, but certainly blizzards are something that we deal with here and that many areas deal with. And impact-wise, certainly a blizzard would have severe impacts on you.
So how far out can we start to see severe and extreme weather like storms or tornadoes start to develop? I'm thinking in particular for things like tornadoes.
We obviously are looking as far out into the future as we can, and we will start to get some sense in many cases of the potential for severe thunderstorms and tornadoes, sometimes many, many days in advance, sometimes 5, 6, 7, 8 days in advance. Now, that far out, we don't have a lot of detail. We have no way to know if a tornado is going to happen for sure, or certainly where or when exactly it's going to happen. But the system of watches, warnings, outlooks that we use in the National Weather Service to convey that risk allows us to put out something called an outlook up to 8 days in advance. Those outlooks are just a heads up message for anybody in the area to say, hey, we don't know the details yet and it may not happen, but keep an eye out on 6 days from now because there's a storm system that could bring severe weather. Obviously, as we get closer to the event, we're looking at more detailed information, more observations. The higher resolution computer models are starting to take a look at the atmosphere and what might happen. So the details in the forecast kind of get fine-tuned as we get closer and closer to the event. But it's not uncommon for us to have an outlook that talks about the potential for severe weather days and days in advance.
So if you were looking out 8 days and trying to spot something that might become severe weather, what might be some red flags that would get your sort of tornado spidey sense tingling?
Well, we're looking at, again, kind of a three-dimensional picture of the atmosphere and getting things to line up in just the right way. Some of the more basic things that we're looking for in our area is typically thunderstorms form along boundaries where there's a difference in the air mass. So our tornadoes frequently happen when there's a lot of warm, moist air over the state of Oklahoma. That warm, moist air typically is driven by southerly winds that bring that moisture all the way from the Gulf of Mexico up over Texas and into Oklahoma. We typically will have some type of front that's associated with an area of low pressure. So we're looking for the presence of maybe a cold front with cold, dry air behind that front that's pushing into that humid, warm air mass that's sitting over Oklahoma. And a third thing that we look for here in Oklahoma very frequently is another type of boundary that's a division between different types of air masses called a dry line. And a dry line separates very warm, humid air to the east and very hot, dry air to the west. And some of our worst weather usually happens where we get all three of those coming together. The cool, dry air from the northwest, the hot, dry air from the southwest, the warm, moist air sitting here. And that's kind of what we're looking for at the surface for severe weather. So as we're looking at computer models days in advance, we're looking for how those things line up. Then we have to also look three-dimensionally and vertically in the atmosphere, and that gets even more complex at that point.
So at what point, as you're starting to watch something like this develop that might be a storm, it might be a tornado, maybe the early ingredients are there to become something that could be severe. At what point do you start to issue out warnings, and at what scale? It sounds like probably internally in the community or in the different offices, that message gets obviously perpetuated a little bit earlier because those are people who know what you're talking about. But I'm assuming at that point you wouldn't start warning the public that a tornado could happen in 8 days.
Well, actually, the system that we use does get information out that's accessible to the public maybe 7 or 8 days in advance. Now, we're not always able to forecast tornadoes that far in advance, but we can see the ingredients coming together. So you may have an outlook that leads up to the tornado day for, several days in advance, increasing in specificity as you get closer. When we get to the day of the event, let's say that today is a tornado day, then probably at some point in the day, we would have a tornado watch in effect. And a tornado watch is a message for the public and for everybody else to say, okay, you really need to watch out because in the next 4 to 6 hours over this relatively small area that we draw on a map, the ingredients are really focusing where we could see tornadoes. It's then where we start watching Doppler radar and we start looking for storm spotters to tell us what's going on in their local communities. The warning would be issued when we think that a tornado is either already happening or is likely to happen. And those warnings are on very, very small time scales, less than an hour, and typically for a very small geographic area. So the specificity of the information starts kind of vague in the days and hours before the tornado and then gets much more specific. And so do the size of the messages or the size of the threat areas that we're outlining for people. But by the time we get to the warning, either the tornado warning is the most urgent message. It means that you need to do something right now to protect yourself.
You mentioned storm spotters and the idea of a tornado watch. Are storm spotters members of the public that are sort of paying attention and you have a connection line with, or these other offices around the area? What are we talking about when we say storm spotters?
It really could be anybody. Storm spotters that we work with in the National Weather Service could be anyone from volunteer firemen to amateur radio operators. There are lots of people that chase storms as a hobby, and they actually serve as storm spotters as well. Anybody who is in the local community who can observe their weather and report that to someone, either the National Weather Service or a local emergency official, really helps us incredibly. And it's 2017 and we're talking about all these high-tech fancy computer models. So it's kind of interesting to think that we still rely on just a citizen in the community to look outside and tell us what's happening, because our detection capability is not good enough yet where we can reliably detect via radar everything that's happening. We still need human eyes and ears out there to tell us what's going on. So storm spotters really are vital to the mission of the Weather Service and getting the word out to people.
If someone's interested in being a storm spotter, is that something that they can volunteer to do? Is there like a training program, or is it just a number they can call if they spot something that looks concerning?
Absolutely. Yeah. The National Weather Service has a program called Skywarn. And if you were to go to the Weather Service website at weather.gov, for example, or search for Skywarn Storm Spotter, Google that, or do a search on Skywarn Storm Spotters, there is a variety of training held at different offices around the country. It's done a little bit differently at each National Weather Service office. And there are 122 local National Weather Service offices scattered around the United States. So find your local office, and they do have training. It's free training, and sometimes it's online. Sometimes you actually go to a classroom setting and sit through a 2-hour class. But I think it's really good, even if you're not going to be a storm spotter, just to learn more about the weather, learn more about what happens, because I think sometimes people get a little too excited or a little too afraid in some cases about what storms may do to them. But when you learn a little bit more about it, you can see that, not all storms are severe. Not all storms are going to produce a tornado, and storm spotters really have the tools to help them kind of tell the difference between the bad storms and the ones that aren't so bad.
So obviously weather is highly probabilistic. There is no such thing as a 100% accurate weather forecast or storm forecast all of the time. So what are the challenges with balancing trying to keep people safe, not sending out too many undue warnings, and keeping people from being unnecessarily anxious about potential severe weather, but also wanting to make sure that people are safe when they need to be safe?
That really is a challenge, and that social media aspect has influenced that work as well. We work very hard to put out the most accurate information we can. Our goal is to tell people what we know when we know it, and give them as much advance notice as we can about something like a tornado. But we have to be very careful to not cry wolf. We have to be very careful to provide information to people to help them make decisions that are based on the best science that we can bring to the effort. And it really is a challenge sometimes to know when to stand up and sound the alarm bell that this is really bad. Last week was kind of bad. This coming week is going to be super bad. And knowing when to do that is a challenge. We take that responsibility very seriously. And of course, we work with a lot of other entities that are doing the same thing. Our partners in local television stations, national television networks, anybody in the media that's getting that word out too. So it's something we pay a lot of attention to and think a lot about. And it really just comes down to, forecaster expertise. What do we think is going to happen? And sometimes conveying that uncertainty is one of the most challenging parts of our job, because we talk about probabilistic information and uncertainty every day. We're scientists, and that's the world that we live in. But a lot of people are looking for a black and white yes or no. Is it going to snow or not? Are we going to get a tornado or not? And we're not there. And sometimes we are more certain about it than others. So learning to convey that information in a language that everybody can understand is a challenge for us.
Rick, thank you. It's been excellent talking with you. And there's just something really fascinating about the weather, I think, because everybody has experience with weather.
That's exactly right. Everybody experiences weather every day, all the time. So it is something that people like to talk about, and people like to criticize the forecast. But I appreciate you having me on to talk a little bit more about how those forecasts and warnings are put together. And there's a lot of dedicated scientists who are working hard to do the best job we can to get you the best weather information. So I appreciate the opportunity to talk about it.
If you want to learn more about Rick Smith or the National Weather Service, we have some links to get you started in the show notes for this episode, which can be found on our website, scienceforthepeople.ca. Up next, we talk with Chris Huntingford, a climate modeler at the Center for Ecology and Hydrology in the UK, about how we're trying to better model our planet's changing climate to get a better idea of what kinds of weather we can expect in the future. Stay tuned.
Every week on Science for the People, we take the latest in scientific progress and relate it to people, our friends, our families, our communities, and our society. And we give researchers, authors, and journalists the time to talk in depth about what matters to them. If you love science but aren't satisfied with sound bites, join us again next week for Science for the People on your local radio station or anytime online at scienceforthepeople.ca.
With me is Chris Huntingford, a climate modeler at the Center for Ecology and Hydrology. His research focuses on the climate system and trying to help with the effort of determining how it might be altered as levels of atmospheric greenhouse gas concentrations rise. Chris, welcome to Science for the People.
Right, well, thank you for inviting me.
So let's first maybe do a quick reminder on our terms. Can you give us a quick run through on the difference between weather and climate?
Okay, so weather is where it's sort of generally quite high frequency, what happens day to day, and you have forecasts of this that will tell you on a specific day, say up to 5 days ahead, what you might expect in terms of rainfall, temperature, how much sunshine. Climate is the same thing, but it's the sort of average properties. So in past climates, present day, and into the future, then understanding climate is really about what's the statistics that you might expect. How many days of rainfall might you expect for a certain location in the world, both now and into the future, if we change the climate. So the two are the same thing, really, but one is just a sort of average statistical properties, whereas weather, or at least weather forecasting, is to give very specific details for the short amount of time ahead.
So would it be kind of fair to think broadly about weather as being about specific events, whereas climate is about broader trends?
It is, but what we want to do in those broader trends is the specific events of concern. So extreme rainfall, for instance. Indeed, we want to know how they will change broadly into the future, but the focus doesn't have to be in the future on the average properties of the weather. You can still talk about what are the statistical likelihoods of, in other words, the chances of extreme rainfall events or extreme temperature events at different decades into the future as we change the climate system.
I want to start by talking about historical climate and weather data. So I'm curious, how far back do we have climate and weather data for? I mean, I assume in order to make predictions about the future, we've got to lean pretty hard on what's happened in the past.
Absolutely, we do. I mean, if you're going to make predictions into the future, then by definition, we're going to have to rely on computer modeling, and that computer modeling has to be trustworthy. So that one of the most obvious things to do is to ensure that for the present climate system, that it can reproduce measurements from around the world. Now, it's a mixed bag, this. So obviously, there's some parts of the world where they were extremely remote until recent years. Some parts of Africa, some parts of South America. So we don't have as many weather stations located in those places as we would like. But we do have a sufficient number, and particularly from around the beginning of the last century onwards. So we have about 115 years of pretty good temperature measurements for sure. And from there, we can indeed see the warming signal, and we can use this to constrain the models. We fit the models to this data. Rainfall data is present, but it's, again, because rainfall tends to have very localized features, then we don't really have enough rain gauges as we would like to be able to understand that. We do now, particularly so, for instance, across the US, across Europe and parts of Asia, then there's a very dense network of rainfall gauges, and we compare our models routinely to this. So, yeah, it's absolutely fundamental, this. We can't project into the future until we trust the models for the present day.
So as we're continuing to use these models, so for example, if we're trying to, if 10 years ago we were trying to model what the climate might look like in 10 years, once those 10 years have passed, are we actually looking at the models that were run and comparing it to what actually happened?
Yeah, we do. So as time goes on, then you have more historical data. You do indeed get a longer time series to compare the models to. And, so the last couple of decades have been very interesting. There was a quite heavy amount of warming up to around year 1998. Then we went through what's been called the hiatus period, where there wasn't any, seemingly the planet wasn't warming anymore. And in the last 3 years, there's been quite heavy levels of warming. Temperature records actually being passed in terms of global average temperature. So that's a very interesting thing. So these models have to get this variability as well, and we think it's in part due to certain features of ocean overturning that were sort of protecting us from the warming.
So setting aside climate change for just a second, how does the process of predicting weather and climate patterns work? We mentioned the use of computer modeling. So can you talk a little bit about how we use computers to model and simulate weather to try and figure out both what's happening now and what might happen in the future?
Yeah. Okay, so the starting point for a lot of this is that there have been quite major advances in terms of weather forecasting. So if you watch a television program on the hour, you tend to get the weather forecast, and they come from computer models of the atmosphere. So that gets things like the pressure levels, the rainfall, the temperature, the momentum, in other words, the wind directions. Now, these computer models that do that, they're on a grid, and they're solved, like you imagine, sort of numerical mesh over the world, and they're solved at different time steps, iterating forward. So we know that these things, weather forecast models, if we set them up with conditions that we can measure now, say today, and we release them to run forward on a computer projecting into the future, then they're generally very accurate for the next 2, 3, 4, 5 days ahead. So the community, looking at environmental things, has developed a confidence in weather forecasting, and then the trick then is to carry that over to climate modeling. Now, The main difference then is that instead of running the model forward for 5 days of model time, you're actually running them forward for years, decades, centuries even. Now, in these equations, what they solve is you have the heat equation, and that links to the amount of different gases in the atmosphere, and these control the amount of heat that's released back out into the atmosphere, which is the greenhouse gas effect. So whereas for weather forecasts, you just keep those constant. Carbon dioxide is not going to change massively over 5 days. The difference is when we take these weather forecast models, we speed them up and we run them for decades ahead. Then in the model time, as the computer iterates forward, we provide different levels of carbon dioxide concentration, and that interacts with the heat equation that's being solved, and then that manifests itself as a general warming.
It seems to me like when we think about modeling an entire planet's climate, that you need to take into consideration an almost unfathomable amount of data points in order to really do this. Because weather and climate, at least based on the information that I've had before, and this could be totally wrong, I could be thinking about this wrong, it seems like a very chaotic thing. And the thing we tend to remember about chaos is that the change in the starting conditions can sometimes bring around really different outcomes.
It does. And that is precisely the issue that we face, is that the system is inherently chaotic. And that's using the sort of mathematical definition of chaos. In other words, if you have slightly different initial conditions and you set 2 computer simulations going into the future, then after about 5 or 6 days, they will diverge. Now, that is actually because the system is built that way. So because you're solving a problem of fluid dynamics, you do get this sort of divergence. But what you do with climate is you hope that if you have enough simulations, then although the system is chaotic, you could actually come up with some sort of probability distribution of what you might expect into the future. So a system can be chaotic, but if you viewed it enough times or enough years, then you get a distribution of, for instance, I don't know, something like how much rainfall you might expect in August in London. Although it's chaotic, you can't predict on any particular year which number it would take. If you sample a chaotic system long enough, then you can build quite robust statistical distributions of what you might expect. And that's the trick with climate modelling, is that we have to come up with these. We can't say specifically, what's going to happen on the 1st of January 2050, but we should get to the point where we can say, well, statistically, we expect in any given year the chance of an extreme event of this magnitude is whatever. So so that's the challenge in it. It's a chaotic system, but to extract from that useful statistics that can then help planners deal with extremes into the future.
So how long have we been using computer models, and how, I'm assuming advances in computing make these models a lot faster or more accurate? And I'm also curious, what did we do before computers, or is modeling only something that's been around since we've had computers to work with?
Well, what happened, this is something you want to talk to something like the UK Met Office about, but before computers were built, so we're talking about in the 1930s, then what tended to happen is, because telephones had been invented by then, or you could travel around the country by train, is people basically sampled, for instance, around the UK, what they looked at the weather that they were experiencing, the direction that it was moving, and then could tell people inland when they might expect a particular weather front to pass. But of course, as time moves on, weather fronts change, so you don't necessarily get an accurate picture inland of what you may have witnessed around the coastline half a day before. Now, as everyone knows, the first computers were built in the Second World War, and I think the first sort of real attempt to use them to make weather forecasting was in the sort of mid-1960s. They were just about fast enough to start providing useful information. Since then, they've just got better and better. I mean, there's many, many things about the weather system that if you have a coarse grid, so if you're solving a coarse numerical grid, which the first computers could only do to operate at a sensible time, then things like rainfall, you have to give average parameters. And what we're getting to now is that supercomputers are so fast that you can even get down to almost modelling clouds moving around and storms in quite a lot of detail. So it's a very exciting time, 60 years of computational input into numerical weather forecasting. We're getting to a new level now where we can do things that certainly couldn't be done before.
So how accurate are some of these models, do we think, especially the ones that are looking long term? Obviously, we don't know for sure because we're predicting the future, and the only way we'll know is once we get to the future. But what's the sort of confidence level in the models that we're seeing come out of some of these computing systems?
Every 6 or 7 years, then there's you get these UN reports on climate change, IPCC, Intergovernmental Panel on Climate Change reports. And one of the first chapters in there is they'll do something for the different seasons. And if you look in the chapters, they'll have a plot on the left-hand side, which is something like the mean temperature you would see and the mean rainfall you would see. And then on the right-hand side, they have the same projections by different computer models, and you can compare the two. And there's a view now that certainly for temperature, it's doing fairly well, but for rainfall, there are still, some major deficiencies. Certainly some parts of the world where, as I understand it, that things like the precise monsoon dynamics are not that well understood. So if you look at rainfall sort of patterns across the equator, they don't always line up with measurements. There's still more to do to get these things right.
Do we have any idea or any theories about why sometimes those seem to be the ones that aren't lining up?
It might be best to talk to someone who's developing these climate models real hands-on, but one of the most difficult things is actually cloud formation and the way small particles in the atmosphere trigger rainfall, the condensation of moisture, exactly what creates storms and the rainfall amounts of certain levels. So there's sort of very detailed atmospheric interactions of humidity and temperature and how rainfall simply falls out the sky. Getting that right is a very difficult thing, and that seems to be the one thing that is causing differences between these models. So people do go out and try and measure these things, and weather balloons go up, and aircraft fly through storms and get as much information as they can. So, but there's still some way to go. Yeah.
I'm curious, does climate modeling take into account things that could cause feedback loops? I'm thinking things like melting permafrost, because there's a lot of stored carbon and methane that could be released when large amounts of permafrost melt. And I'm assuming those kinds of feedback loops are definitely going to affect the model for sure.
Yes, so climate models, until fairly recently, were referred to as things called GCMs, which is general circulation models, and so the point being that they were getting the circulations of the atmosphere. But now the name they're generally called is Earth system models, and the point being that yes, they get the biogeochemical cycling in. So things like the permafrost releasing carbon and methane into the atmosphere at different temperatures. That's being modelled. Other examples include loss of sea ice. The sea ice cover is going to be less into the future, and what will that do in terms of reflectivity of the planet, because the sort of ocean is less reflective than the ice. That's a feedback. There's also feedbacks in the carbon cycle themselves, which are things. So, for instance, the one theory is that if you've got sufficiently warm parts of the tropical rainforest would die back. You just won't be able to cope with the additional warmth. Now, in that dieback process, what that means is trees die, they don't grow to the same level. The carbon falls onto the ground, and then it's slowly released back as it sort of respires back into the atmosphere. There's a lot of these feedbacks, and the hope is that at least we have some idea of what they might be. There's always a worry that there's one that we don't include that suddenly becomes very important that people haven't thought of yet. There's a lot of them, yes. So exactly, yes, that's why they're now called system models rather than circulation models, which just refer to the sort of broad meteorology.
It occurs to me that the process and the project of modeling a climate, it must be so massively interdisciplinary because you require both people with computing skills, you need mathematical skills, you need people who are comfortable with air dynamics and fluid dynamics, you need skill sets in ocean systems, you need skill sets in geology and how, we're talking about permafrost, you need to know how much stored carbon's down there. Massively interdisciplinary project, which I'm not sure that I had really ever fully appreciated.
Yes, absolutely. I mean, so for instance, in the United Kingdom, we have the Meteorological Office do build these system models, but they pull in people from my laboratory that do the Ecology and Hydrology, the Oceanic Centre down in Southampton, the Antarctic Survey. They provide information for the polar responses. Yes, it is. You do need meteorologists, along with all the other disciplines you mentioned, and you could almost argue that you may even need social scientists. That if there were feedbacks in the system where climate changed so much that people really were alarmed, and there was an incredible move towards, say, green technologies, then that affects emissions, and that would affect the CO2 concentrations in your modelled future in these models. So the human interaction and the feedback is something that's not in yet, but when that comes, that means we will also need social scientists looking at these models as well.
Just so many little moving pieces of that puzzle. It boggles my mind sometimes when I start to think about all the little details that need to be included. It's an interesting move sometimes in science, because we think of science as being really reductive, as something where we kind of pull something apart and look at the little pieces of it and figure out how those little pieces work, how a cell works, how an atom works, how very small bits. And climate is inherently about the system. It's inherently about what happens to all of those little pieces when they interact together, not just two of them or three of them, but all of them. And so trying to both think about all of the pieces involved and then also figure out how they interact together and get that all modeled and simulating in a way that we can have confidence in it. It's such a feat to undertake.
Well, it is, but it has problems as well. I mean, I think the progression has been amazing, and I certainly never want to knock what's been done. But it's there is a problem that there's an argument that these things have become so complex that even the people that build them don't fully understand them now, because there's so many interactions. So if, for instance, rainfall or temperatures have particular features into your projections into the future, it's not always easy to understand the exact local processes responding to global warming that have caused that. So you're right. Yes, I mean, certainly they're coupled together, and it is all about the couplings, not just the local processes. But in a way, a lot of these models have become a bit like black boxes, and there needs to be a move now to perhaps pick them apart a bit more to really understand internally what they project as interactions. So and the reason for this is it's not in any way to criticize climate science. It's just that, as you say, most things you do in a sort of reductive form. And I remember when I was a mathematician by training that, the message then was always, you don't ever look at a more complex problem until you can understand the simplest one first. You just don't do that. So you understand in small detail something, and then if there's something coupled to it, you look at that coupling, but just that coupling, and then you add the extra bits. Now, the issue with climate change is that because it is a fully coupled system, and because our politicians pressure us to get answers quickly, and rightly so, to get some idea of what we might expect into the future, then we've had to take a very, very different path to the conventional scientific path that would be taken, which is to bolt all these things together quickly and see what happens. So it's exciting. It's not the normal way you would do science, but that's because there is this pressure to find answers quickly.
So what kind of variety do we see when we run these simulations and models repeatedly? Are the simulated outcomes trending generally in the same direction? I mean, do they vary wildly and kind of conflict with each other? What are some of the outcomes that we're seeing as we model these with increasing amount of data and sort of increasing fidelity?
Well, certainly, again, I'll refer back to these UN reports, which you can go and buy them. They're a standard book you can buy, and in them you do see certain parts of the world where some climate models project are going to get wetter and some are going to get drier. So that's a very difficult thing. How do you plan based on that? When you were talking earlier about the extremes, then there's a very interesting thing that's been done in Oxford University where they just took one model and they looked at the sort of chaotic features, and they used a sort of citizen science thing where you can actually run the climate model on your PC at home, and each person that signed up to do this had slightly different initial conditions, and then that gives you a spread of different projections into the future. So we know from looking at these UN reports, all the different climate modelling centres around the world, that they contribute. There are differences, but even if we just look at one single model, then you can get quite big differences between them. If you run them enough, then you get back to this issue that it's a chaotic system, and you can populate the probability, what's called a probability density function. But if you just look at the spread that they get this citizen science system in Oxford, it's very, very interesting. Yeah, so chaos. So that's the whole problem about climate change, is that you're trying to project a mean change into the future, but with a system that has inherent, quite long, up to decadal timescale internal variability as well. So we're really after what's the mean change that you would expect to see over centuries ahead.
So with
in response to human,
with the most recent, some of the recent events that have happened in particular, there's been a number of hurricanes right now as we're talking. We're sort of in between Harvey and Irma potentially hitting the U.S., which are two. Harvey was a very large hurricane. Irma's potentially even bigger, depending on how things go. There's been massive flooding. Southeast Asia's been hit by a massive flood in their monsoon season. And there's a lot of discussion about whether or not climate change is contributing to the frequency or potentially the extremeness of some of these major weather events that we see. So what do some of the models that we look at tell us about that question? Is it even possible for us to look at models and get an answer for that question?
Indeed. We've been talking about exactly that question earlier today. So it's called the attribution question. So if you had a very fine resolution model that was doing very well at getting hurricane tracks, and you ran that, say, thousands of times, slightly different starting conditions for current levels of carbon dioxide in the atmosphere. And if you did it again, thousands of times for pre-industrial levels of carbon dioxide, and then you would look at the average direction the tracks the storms take, or you would look at, for a given trajectory, what's the intensity? So has the intensity changed? So the question you ask is precisely the challenge for climate modelers at the moment. Now, the issue is that to get things like that very accurate, you need in the computer a very fine mesh. However you cover the world, you might be looking at a mesh of that you're solving your equations on of just 5 kilometers over the whole world to get storm tracks accurate. The issue is that despite amazing progression in computational speed processors that you can buy, they're still not fast enough to allow us to do that. So ideally, you would have a very high resolution weather forecasting model that we know gets storm tracks right, and run that for thousands of model years, both for current CO2 and pre-industrial, and that would answer the question. That would answer your question. But computationally, we're not there yet. And in fact, there's going to be some talking about this over the next few weeks as to exactly how fast will computers have to be before we could answer that question.
It's also not just a question of does something like a hurricane happen more often, but also does a hurricane that's going to hit a city or a populated urban area going to happen more often? Because if they happen out in the middle of the Pacific Ocean but dissipate by the time they get to shore, they're sort of less of a concern, I would expect.
Yes, so again, this is where the social scientists would be very useful to have, because what will happen is that you could run these computer models again for pre-industrial now, and then you would look at the tracks and you would place particular emphasis on what's the probability of, say, an increased intensity or more tracks actually hitting places of major urbanization and also into the future where we think people are going to live. So so it would be done in a way that it would be done in that way. And so then what that allows you to say is if you project that a certain part of the world is going to be hit twice as often, and for a given storm how much that's costing dollars or risk to life, then suddenly you can attribute, you can say, well, the raised CO2 in the atmosphere is costing us X $million extra per year. So there's always been hurricanes, but there's reason to believe that they may be hitting certain parts more frequently. I mean, it could be, and we don't know for sure, that it's the opposite. In fact, that climate change could move hurricanes, as you say, away from centres of urbanisation. But, not every single thing associated with climate change is bad news, but we need the answers so we can plan.
So for someone who is really interested in following some of the latest information that's coming out of climate models, I'm curious, what to you is the most exciting? What's the thing that has most interested you or that you found most interesting in the field in either the last couple of years or looking out into maybe what's possible in the next couple of years?
Well, I think the technical side of it, the advancement in computing has been remarkable, and it allows us to do things and understand things we wouldn't otherwise be able to do. I think also there's a feeling that a lot of these climate models have become very complex and like black boxes, and in a sense, can we reverse engineer them? So what new bits of mathematics can we bring to their outputs that when we collectively look across models, we can find common features between them? So what can we say with confidence of changes we expect into the future? So that's becoming a big thing now, that you have all these different climate models. How do you reduce the variability between them? I think scientifically what it's done is quite amazing. It's forced people, as you said earlier, not just meteorologists, but other Earth system modelers to really think in the bigger, the larger scale. And so, we're getting real sort of exciting things, finding out about how vegetation functions and how photosynthesis, things that people used to learn at school, but these computer models, because we have to get this stuff distilled down to a set of equations that can go in these models, it's forced people to really focus on, how do trees in effect respond to different droughts, things like that. Getting that precisely right, the rooting depth and the sort of hormonal signals through them and how they cause leaves to change and the phenology, all these things, it's really focused quite incredibly, multiple disciplines at coming up with what's to zero order. So what's the main thing they expect to see changing into the future? Yeah, so I think that's the most exciting bit, last 10 years. Yeah. I'm
curious, do people ever sort of provide information to the model where they think maybe it's not relevant, but it might be? Let's see if it changes anything, and just kind of like give the model a set of data to see if it actually has an impact?
Yeah. Oh, yeah. I mean, yes, absolutely. We do that all the time because sometimes there's something that we don't fully understand, and so we'll take a range of values for. So there's something that you want to parameterize, you want to write as an equation, but there's an uncertainty in it, and you will try a range of different values. Now, if we find that makes the model really diverge, so you try an upper, medium, and low value, upper, medium, and low value of some number describing, say, an ecological response. If you then put that in these climate models and you get very divergent behavior, then what that's basically saying is you need a set of field experiments. You need people to go out and measure that very accurately. Yeah, so a lot of that does go on. Not as much as would be ideal, because the issue that these computer models are so, they just eat up computing power, and there's only so many supercomputers in the world. So, yeah. Is
there a particular thing that's been thrown into a model that has had an important effect that you can think of that was kind of like unexpected, or you went, oh, that's interesting, never would have thought of that?
Well, I think certainly from the ecological response, there was this paper produced many, many years ago. I wasn't involved, but it was by a colleague, and where they found that you could indeed get the rainforest, a lot of the tropics would just collapse if you reached a certain level of warming. I would say that was quite iconic. I think you mentioned it yourself, some of the permafrost feedbacks are quite strong. And I think one of the things that, just going back to rainfall, is that for every degree of global warming, the world gets about 1% wetter. So you invigorate the hydrological cycle through enhanced evaporation off the oceans by about 1%. But extremes are different, and there's reason to believe the intensity of them go up by about 7% every degree of global warming. So there's some suggestion that there's something different between extremes and mean rainfall amounts. Now, this has been seen in the data, and a lot of the climate models are starting to show that. So that's very encouraging, I think. So that's when it's most encouraging, when I think someone sees something in the measurement, alerts to it, and then you get the computer models to explain it.
Chris, it's a really fascinating field with so many depths, I think, that we could plumb. But unfortunately, sir, we are out of time. Thank you so much for the discussion and for your time this afternoon. Really interesting topic.
Yep, well, you're very welcome indeed. And thank you for having me on your program.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.